The tackling missing beans define the functional coverage in SystemVerilog for the deterministic coverage closure. The abstract. In the context of the hardware design verification, defining functional coverage accurately in SystemVerilog remains a challenge, often due to human errors leading to missing bins. This paper introduces a methodology aimed at enhancing the functional coverage by identifying these overlooked bins, by treating coverage bins as a SystemVerilog queue and employing a waiver function. This approach provides verification engineers a mechanism to efficiently determine whether assembled coverage bins are already accounted for in the coverage. Experimental validation involving cache managing IP underscored the method's efficacy. The result revealed 14.1% of the missing binaries among the coverage holes using our proposed methodology, culminating in a 6.0% overall improvement in functional coverage. Thus, the proposed method not only rectified human-induced inaccuracy but also improved the overall robustness of the hardware verification. Introduction. In the context of the functional coverage, despite achieving the 100% functional coverage, bugs may still manifest. In such instances, verification engineers can find themselves perplexed, unable to pinpoint the oversight that led to these unexpected issues. Consequently, they are left with the disconcerting the realization that they may not be able to confidently respond to the questions. Is verification truly completed? This paper addresses the inherent challenges tied to defining functional coverage in SystemVerilog, emphasizing the problems that arise due to the human errors, notably the oversight of the missing bins. These are data bins that should identically be part of the coverage but are unintentionally omitted. The core of this study revolved around proposing an efficient methodology to solve the recurring problem of defining the functional coverage in SystemVerilog. The approach we propose is easily applicable due to its reliance on the functional fundamentally SystemVerilog syntax. This represented the methodology targeted toward achieving the exhaustive coverage closure. The primary aim is to ensure a comprehensive approach to coverage, leaving no aspect unaddressed, thereby enhancing the overall quality of the verification process. The rest of this paper is composed as follows. Section 2 introduced the challenges that arise when defining functional coverage and highlighted the debugging difficulty in encounter with the conventional method. So Section 3 pertained to relevant background and research. Section 4 proposed a three-step method for composing the functional coverage to address these challenges. So, Section 4 demonstration the efficiency demonstrate the effectiveness of this approach when applied to real-world cases. Through the experiment, it is possible to ascertain the thoroughness of the validation by using the proposed methodology to confirm the potential outputs of the cache managing the intellectual property IP. Finally, it provides a conclusion and outlines the potential future work. The problem statement illustrated in Figure 1 is the comprehensive set of the coverage bins, each representing the possible scenarios within a coverage point. This figure shows cases the complexity surrounding the definition of the coverage bins. Key sets are defined in the universal set U, encompassing all potential coverage bins within a coverage point and the ideal set I, representing the desired coverage, the defined set D. The coverage bins explicitly identified by engineers for verification, and the sampled set S, showcasing the coverage bins sampled during test. The coverage bins in the diagram are divided into 5 types, each of which has a specific meaning, as described in Table 1. Covered bin indicates the item sampled by the test is covered by a coverage bin defined by the engineer. Excluded bins are coverage bins that are neither in the ideal set nor the defined set. Uncovered bins are those that have not yet been tested because of the lack of the test scenarios. So this is Figure 1, coverage point and coverage bins diagram. Table 1 is meaning of the 5 coverage bins types. So the objective is to transition all coverage bins bearing the excluded ones into covered bins. Ideally, a good alignment between the ideal, defined, and sampled set is sought. This demanded the engineer to meticulously adjust the defined set, ensuring the absence of the missing bins and missed included bins and missed excluded bins emerge from the human errors, representing ideally non-culpable bins mistakenly defined in the coverage point. Their presence prohibits reaching 100% coverage. So on the other hand, missing bins refer to those bins that, despite being tested, aren't, including the coverage point due to the oversight or over-exclusions. Their presence can falsely indicate comprehensive testing and leaving the potential gaps in verification. Our traditional approach to address that is the illegal bins keyword illegal_bins keyword, which triggers notification upon activation. However, its uncontrollable controlled reporting poses challenges. When solely utilizing the illegal_bins keyword, it becomes challenging to pinpoint the specific times and rules under which illegal bins were triggered. In addition, it is necessary to use the electronic design automation (EDA) tools to define if you have hit any illegal bins. This complexity not only hinders debugging but also ultimately extends the time required to achieve a coverage closure. So in essence, there is a lack of a straightforward mechanism to prevent the reporting of errors in this context. Given that the illegal bins manifest as errors, there exists a potential for test failure associated with their presence. Chapter 3 is background. In other research related to functional coverage, it's been suggested that a validation is necessary to ensure all generated coverage bins are reachable. The Functional Coverage Management System (FCMS) automatically converts table-based specification into coverage, while the previous work has the advantage of being able to generate a system-value assertion (SVA) model for formal verification and a system-value functional coverage model for simulation verification. It requires the use of the separate tools called SpecGen and suffers from performance drop of about 30%. The method we propose focuses on detecting missing bins, and it can be easily and simply applied by just changing the way the system value function coverage is written. When using our method, the performance degradation occurs within 3%, which is approximately 10 times less compared to the conventional work. So several EDA tools provide features for the analysis of functional coverage, like merging coverage from multiple runs. They also provide various insight from the perspective of analyzing cross coverage, For instance, the vManager has an aggregate analysis feature that analyzes the uncovered bins of the crossing coverage, making it easy to understand the patterns of uncovered bins. It also shows whether the excluded coverage bin like ignore underscore bins and illegal bins have been hit, along with their scores. However, it does not provide information on which test and at what time the excluded bins were hit. When verification engineers become aware of the existence of the missing bins, they need to check through which scenario that coverage bin was covered for accurate analysis. Our proposed method enhances the EDA tool by incorporating a feature to analyze the missing bins which was not previously available. This new functionality provides detailed log information when missing bins occur. This saves the verification engineers time in determining whether missing bins are reachable. So meanwhile, the EDA tool remains the primary source for analyzed uncovered bins. Chapter 4 Proposed Solution. To achieve exhaustive coverage closure, we use a process of iteratively modifying the coverage model to find and correct the differences from the ideal coverage. Figure 2 depicts the process of modifying coverage. Initially, the functional coverage defined, so the coverage model initially designated is highly likely to include holes, indicating the coverage that was inaccurately defined at the beginning. After conducting the test, the engineer analyzes the coverage result. When analyzing bins not covered in the coverage result, those deemed incapable of being covered are classified as uncovered bins, while those assessed as coverable are labeled with excluded bins. If a bin is determined to be an uncovered bin, we enhance the uh, test scenario. If it's classified as a missed excluded bin, we add the bin to the waiver conditions. So the uncovered bins can be easily detected using the traditional method of EDA tools. The method we propose should be used in conjunction with EDA tool approach, and it complements the existing methods. Following the state-of-the-art methodology for functional coverage creation, the engineers can review reports on missing bins. If it is feasible to cover the reported missing bins, they are removed from the condition of the waiver function. If coverage is indeed impossible, it necessitates an investigation into potential issues within the design or verification environment. If the coverage does not reach 100% or there are still missing bins, the process reverts to the run test stage, and the following steps are repeated. However, if the coverage becomes 100% and there are no longer any missing bins, the process terminated and the coverage at that point is deemed the final coverage. Though through this iterative process of refining coverage, tests are executed repeatedly to bolster coverage. Figure 2 Process of refining coverage. This paper introduces a three-step approach to writing functional coverage in SystemVerilog. Through this methodology, engineers can effectively detect missing bins with ease. This approach purely leverages the coverage syntax of the SystemVerilog. The relevant code snippets are provided in Figure 3 and 4 and 5. So, A. Define coverage bins in queue. The first step involves defining the desired coverage bin within a queue. So specific data structure and SystemVerilog, the data pushed into a queue constitute the coverage point for crossing coverage. The reason for defining coverage using the queue is to use ignore underscore bins flexibly and reactively in cross coverage. As illustrated in Figure 3, a queue named state cover bin is defined with the capability to store 10-bit data. This is done to establish a cross coverage that intersects the 10th coverage point of 1 bit. A critical component of this process is the waiver function, so determining if the data is reachable and ensuring only valid data is entered into the queue. This function, apart from the verifying data, also offers reusability across the multiple coverage points can be utilized across various scopes or classes. The code snippet includes a waiver function named waiver state. This function takes 10-bit data as input and provides an illegal IDX as output. If, in the engineer's judgment, input data is feasible to be covered, the illegal IDX is output as 0. If not, a value can be checked to see which rule includes it in the illegal condition. For all conceivable states corresponding to the universal set, only those assessed as coverable with the result of the zero from wave set function are placed in the state cover bins. The Q now represent the defined set. Section B, define a cross coverage using cross Q type. The subsequent phase is about defining cross coverage using the cross Q type keyword. It is a SystemVerilog keyword utilizing the automatic define of the queues of the top tuples within each cross. Our unique approach is to convert the queue used in step A to cross queue type to define the ignore bins in cross coverage. This type of bin is advantageous for specifying bins for exclusion. A unique function, create ignore bins, is defined to return a cross queue type. This function pushes all non-included instances from the queue, ensuring that only the necessary coverage bins are retained in the cross coverage. As depicted in Figure 4, we have defined 10 coverage points from S9 to S0 as cross-select coverage. The S9 to S0 are coverage points created by dividing the sampled 10-bit data into 10 bins, each consists of 1 bit. The create ignore bins function incorporates into the output cross queue type only those states that are not present in the solid cover bins. The keyword ignores bins is utilized for the cross coverage bins that are the outcome of the create ignore bin function to exclude them from coverage. This procedure allows for a transformation of the states defined in the state cover bins into cross coverage bin format. C. Reporting the missing bins pre-sampling. The concluding step is about inspecting the potential missing bins before sampling. The data intended for sampling is fed into the previously mentioned waiver function. So this process identified if the data should be included. If the inclusion is deemed necessary, the return value from the waiver function exceeds 0, indicating the data pertained in the missing bins. Such data is then reported via an array syntax, allowing verification engineers to quickly detect the presence of data from these missing bins in the logs. As a demonstration in Figure 5, the waiver state function is utilized to procure the uh, RESP response state, the dataset for sampling as an input and yielding the illegal IDX as an output. The implication of the illegal IDX index, the exceeding 0 signify a state where coverage is impossible. In such scenarios, an error statement is employed to report the situation. The method of the reporting is subject to either modification depending on the configuration. This data's subsequent discovery facilitates an evaluation of coverage definitions accuracy. Any discrepancies observed lead to modification in coverage definition or in the test cases, thus refining the coverage reliability and enhancing verification quality. The figure 3 is defining coverage bins in Q. As figure 4 is defining cross coverage using cross Q type. Figure 5 is reporting missing bins pre-sampling define. The Chapter 5 Experimental Result. Section Experimental Setup. A series of tests were conducted to validate the effectiveness of the proposed method. These involved the design under test duty diagram showcasing the structure of the CacheManager (CM), a pivotal IP managing caches and their states. The figure 6 effectively illustrates the command flow of the CM, and the CM incorporated modules referred to as statements and several cache entries. These cache entries possess their 10-bit state, with each bit carrying a distinct meaning. For instance, the 80th bit could represent the latest or latest, and while the first bit may signify Dory, the state transitions invariably occur due to the state machine. The figure 6, the command flow of the CacheManager. The state machine module is a type of deterministic finite state machine. There exist two types of the state machines in CM. State machine _curr is utilized to modify the state of the cache currently being processed, while the state machine _infl is used to alter the state of the neighboring the cache influenced by the cache currently being processed. If the affected cache does not exist, state machine _infl will not work. The CM receives as input the index of the cache that needs to be currently processed, currently cache ID, and the cache influenced by it influenced the cache ID. Along with the command showing the input, the state machines receive the request state from the cache entry determined from each respective cache ID as REQ state _CURR and REQ state _INFL accompanied by the CMD input serving as an input. A state transition table is embedded within the state machine. This table describes information on how to modify the state based on the combination of command and request state. That is, which bit to set or clear, and what output command CMD output to produce. The altered state following the guideline of the state transition table are outputted from the state machines as alias state _cu current CURR and alias state _INFR. Subsequently, these states are stored as the state of the corresponding cache entries. During the testing process, we implemented the sampling each time an output of alias state was generated to confirm that every conceivable state had been transformed. The optimal strategy to examine the entire sample saves a space of potential coverage ideal set is to predict every incoming command line and each respective state. However, this approach encounters issues due to the following reasons. The commands are received in a non-sequential or random order, so the input command is determined not only by the preceding output command but also by other external modules to the CM. The three is state transition can occur in either the state machine underscore current or state machine underscore info. To predict the subsequent state, it is necessary to know the previous state as well as the upcoming input command. For the non-deterministic nature of such input, engineers are unable to define perfect coverage from the outset, which introduces the possibility of the human error. Hence, we employ an approach of initially defining coverage for simple scenarios, then enhancing the coverage through repeated testing utilizing the method in section 3. So section result. The table 2 pertains to the result of our experiment. The experiment saw the cross coverages resulting in a total of 2048 states when all possible cases were examined. The study revealed the complexities when isolating the ideal set I, a set of valid states, from the universal set U, given the state transition table elucidated the with transformations without dealing with the resulting RSP state. This complexity stems from the complex interplay between a myriad of the input combination of REQ state. For the sake of the efficiency, the team initially outlined the coverage for basic scenarios, namely initially defined set D init, and then they improved the coverage iteratively based on tests. As a result, the initially sampled set as init for the RESP state underscore core and RESP state underscore info was found to be a 202 in RESP state core and 119 in RESP state in full out of a defined 304 and 296 bins, respectively. It implies that the initial coverage defined and the test scenarios only cover for 53.5% of the total. After refining the coverage using our proposed method, we were able to achieve 100% coverage with 228 coverage bins derived from the RESP state core and 165 for RESP state info, which we have termed the final defined set, definer. Having achieved 100% coverage and with no further missing bins emerging, we concluded the final defined set is identical to the final sampled set, the S-final, and the latter being the collection of the samples obtained from the final set. Since the final defined set and the final sampled set are the same, we were able to designate them as the ideal set. Comparing the initial defined set with the final defined set, there were 380 overlapping coverage bins, confirming that the initially defined set has an accuracy of 63.3%, a figure derived by dividing the overlapping coverage bin by total size of the initially defined set. Table 2 is the size of the coverage set. Throughout the process of improving the coverage using the method proposed in section 3, we tackled the uncovered bins by analyzing their properties to define whether they fit within the ideal set by tracking the transition of the previous state, and the engineer could verify verify if the input commands were received in a correct. Oh yes, engineer will engineer could verify if the command were received in correct sequence and determine whether the state could indeed be covered. If a bin was not covered but could not be covered, the test scenarios the could be covered. The scenarios were constructed to cover these bins. If a bin was not covered and could not ideally be covered, they were earmarked in the wave function on the wave function waiver function. So effectively over-excluding them. By deploying the methodology proposed, listing bins that should have been incorporated but weren't due to the human errors were identified and a corresponding condition was removed from the waiver function. So the results were encouraging the reporting table 3. The paper's methodology assisted in efficiently uncovering the 14.1% of the bins that would have been overlooked using a conventional techniques. Out of 255 total coverage holes, 14 and 22 22 right 14 and 22 missing bins were detected respectively, which represent a proportion of 14.1%. The remainder are initially uncovered bins that can be verified using traditional methods. There were the 35 uncovered bins due to the scenarios deficiencies and 184 missed excluded bins requires exclusion. Rivaling our proposed method arms verification engineers with a reliable strategy to identify and rectify missing bins. Figure 7 illustrated the importance of eliminating missing bins in the process of enhancing the accuracy of functional coverage. Through our experiment, we were able to discover a total of 7 register transfer level RTL as well as related to missing bins. Upon examining the result of the experiment, it was found that the method enabled the identification of the total of 36 missing bins out of the initially defined 600 coverage bins, equivalent to a 0.6.0%. This indicates an enhancement of the 6.0% in the overall quality of the functional coverage, a significant improvement attributed to the implementation of our proposed method. The table 3 is analyzing the number of coverage bins with holes. The proportion of the missing bins is 14.1%. And the next one is the figure 7 is coverage bin set before and after refinement. Chapter 6 is conclusion and future work. This paper introduced a methodology, a writing functional coverage that effectively detects missing bins caused by human error. This methodology is motivated by the intention to confirm which functionality of the design have been thoroughly verified. Despite achieving 100% coverage, the existence of these missing bins raises questions about the need for additional testing. To address this issue, we propose a methodology that defines a waiver function to describe the condition of the bins that cannot be covered and verified whether a bin can be covered through the waiver function before sampling the coverage bin. This method, which exclusively utilizes the SystemVerilog syntax, offers the advantage of being easy to use. Through the proposed method, engineers can identify and eliminate the missing bins, therefore enhancing the completeness of functional coverage. In the experiment, this methodology was used for the verification of the deterministic final state machine, detecting the total 36 missing bins, thereby enhancing the overall verification completeness by 6.0%. The application of our proposed method had been demonstrating effectiveness in addressing the coverage point that demanded thorough validation. For simpler coverage point, conventional method can be consistently applied without encountering any issues. Our proposed methodology is versatile, allowing for the sampling of not only 10-bit data, but also of the data in varying formats, including structures on object-oriented data. When defining transition bins to verify the command order, human error may occur during the functional coverage definition process. This methodology is capable of counteracting this by identifying missing bins during the transition bin definition. A distinct advantage of utilizing the proposed method for the functional coverage is its ability to detect previously overlooked missing bins. Nevertheless, the process necessitates the engineer's intervention to validate whether the coverage bin corresponding to the missing bins resides in the either set. As a future development, we plan to research enabling the reactive coverage closure through the script automation. Through the automation, we aim to demonstrate the necessity for human invention in detecting if a coverage bin belongs to the ideal set. This advancement aims to streamline the process and enhance the efficiency of coverage closure tasks. Okay, so there are five references. Okay. Today I read this paper titled "The Tackling Missing Bins: Refining Functional Coverage in SystemVerilog for Deterministic Coverage Closure." Okay, thank you for your time. See you next time.